Okay, we're now on to chapter 10 from Pure Year 2, which is numerical methods. We'll just be looking at iteration and the Newton-Raphson method. So we're going to go straight in with how do you find a root, how do you locate a root, and then we'll do some bits on finding iterative formulae. But to begin with, let's look at these little boxes that we've got, our kind of summary boxes here. So for locating roots, to show that a function has a root in the interval a, b, we need to show that there is a change in sign. So we need to say that the f of a and f of b have opposite signs, meaning one is positive and one is negative. And f of x must be continuous over the interval. Now, what I mean by this very, very quickly is if I had a graph that was, say, looked like this, and here is my interval a, b, well, clearly there's an asymptote here. So there is not actually going to be, this is not a continuous function because it kind of jumps in between it. Maybe it would have been better if I said like the graph was down here, because clearly we can see that it has gone from being positive up here to negative down here, but there is an asymptote that is going with it, so it is not a continuous function. A continuous function over AB is just a kind of typical one where between those two lines that we've got there, the line is unbroken. So that's all we mean when we talk about something being a continuous function. And then if we wanted to show that a root is correct to a certain degree of accuracy, we just need to carefully consider the interval to test. So for 1.3 to one decimal place, you're going to think, what is the smallest thing that I need to test for 1.3 that would round to 1.3? Well, it would be 1.25 for the lower end. And then for the upper end, it would be 1.35, because everything inside this interval 1.25 to 1.35 will round to 1.3. Of course, 1.35 would round to 1.4, but really what we're wanting to test is 1.34999999. So we might as well test 1.35. And if I wanted to do, say, 1.24 to three significant figures, well, I would do for the lower kind of interval part that we're going to have, I would do a 0.5 lower, so that's 1.235 for the lower part, and then 1.245 for the upper part. And in fact, it's often easier to find the upper part first because you're just adding on an extra 5 to the end, and then you're just kind of bumping it down for this end here. Okay, we'll have a look at how you find an iterative formula as well. So if you want to find your own iterative formula, you set the function equal to 0 because you're trying to find a root, and then you rewrite it in the form x equals g of x. So you try and make one of the x's kind of the subject, but it's still going to be in terms of x. And there are often multiple ways of doing this, and working backwards can help if it's a slightly trickier one. Now, when we're talking about finding roots, we're often talking about where something is crossing the axis, but if they're talking about a minimum or a maximum point, you may need to do some differentiation first, and then you're finding the root of that derivative function, because the root of a derivative function is where the function is equal to 0, in other words, where the gradient is 0, so it has a turning point. But I haven't done any of those questions in this particular sort of chapter summary, but do look out for it if it's not referring to a root. It could be talking about a maximum or a minimum, where you need to do some differentiation first. And we'll cover this exam tip when we go through this part A of this question. So let's have a look at this one. This is a question that's across two slides here. Part A, it says, show that the function f of x equals x cubed minus 3 brackets x plus 1 minus the cube root of x has a root alpha in the interval 1, 3. So really easy for this. We will just begin by doing f of 1, which is very easy. It's just going to be 1 cubed minus 3 brackets 1 plus 1, which is 2, minus the cube root of 1. What's that? 1 minus 6 minus 1. 1 minus 1 is 0, so it's just minus 6. Didn't even need to touch the calculator. And then I'll also do f of 3. I'll probably need the calculator for this one. It's going to be 3 cubed minus 3 times 3 plus 1 minus the cube root of 3. So on my calculator, what's that? 27 minus 12 minus the cube root of 3. We get 13.557. So I'm going to say change of sign and f of x is continuous over the interval, hence a root alpha is in the interval 1, to 3. And this is what my exam tip is down here. Make sure that you state that the function is continuous over the interval. That's always part of what they're looking for in these kinds of questions. If you're not sure if it's continuous or not, it pretty much is going to be. It's only going to be the asymptotes if we have things with like the reciprocal functions, but all of these things here are just continuous lines, so I wouldn't worry about too much whether it's going to be continuous or not. I would say pretty much all the time it is going to be. Further, and they would never do this in one question, but I'm trying to demonstrate as much as I can here. Further, show that alpha equals 2.222 to 3 decimal places. So 3 decimal places for 2.222. I'm going to need to test a lower bound and an upper bound. Now the lower bound is going to be 2.2215. And then when I calculate the upper, it's going to be 2.2225. So on my calculator, it's going to be 2.2215 cubed minus, where's it gone? Minus 3 lots of 2.2215 plus 1 minus the cube root of 2.2215. And I'm going to type that in carefully because then I can just go back through on my calculator. And anywhere there is this like 1, clearly that's just going to get changed to a 2 in this next part that we have over here. So I'm just going to type it in super carefully so that I can change it in just a moment. So that's 2.2215 cubed minus 3 brackets 2.2215 plus 1 minus the cube root of 2.2215. This one gives me minus 6.0737 blah 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 times 10 to the minus 3. If you can't remember standard form, you can leave it in standard form. But this is 0.0060 blah blah blah. Okay, that decimal point has moved 3 places. This one I'm not going to show the full substitution because by this point the examiner does know what I'm doing. So I'm just going to go back, and anywhere I've got those yellow ones, I'm just going to change them to 2s so that I'm saving a little bit of typing on my calculator. And I'm hopefully going to get a positive one here, and I do. I get 5.542 times 10 to the minus 3, so we've got our 0.00542 like this. So I'm going to say, I could say that this one is less than 0, this one is greater than 0, so I have change in sign, continuous function. I'd probably give a bit more detail if I was doing it in the exam. Hence, alpha equals 2.222 to 3 decimal places, because if I know the root is in between these two numbers, well, all of these numbers round to 2.222 to 3 decimal places, so that must be what the root is for that part. Now for part C, it says show that f of x equals 0 can be written in this form. So our f of x is going to be equal to 0. It is x cubed minus 3 lots of x plus 1 minus the cube root of x. Just double checking I've got that right there. I do. So I just need to see how they've done a rearranging. Now this is pretty obvious what they've done for their rearranging because of this big cube root sign. But if you did need to work backwards, you could say to yourself, well, if I cube both sides, I get that x cubed is equal to 3x plus 3 plus the cube root of x. And it becomes a little bit easier to see how this red part is linked to this one. This is a particularly easy one, but if you did want to work backwards, which is what I'd suggested down here in the box, that working backwards can be really helpful to get yourself from the iterative formula back to the original function. So it looks like I need to put everything else onto the right hand side. So that is my 3x plus 1 onto the left hand side, the cube root of x, and that is equal to x cubed. Now when I cube root both sides, I would then have the 3x plus 3 when I expand the brackets. I get the cube root of x, and then that overall thing, if I can do it a little bit neater than that, is also being cube rooted. So that's the first half of the question. Now in the second half of the question, we will continue, but we're also going to be having a look at the actual iteration process, which I haven't really gone through in much detail in the boxes over here because it's pretty straightforward, and the staircase and cobweb diagram. So I'll come to the staircase and cobweb diagrams when we do part E and part F. So using the iterative formula, look how this thing that we've just done is the same as this thing here, apart from this x is now x of n plus 1, the next thing, and where we have the x here and here, those are both xn. So we're going to use this iterative formula we've just created in part C with our first value of x, x1, as being equal to 1. We're going to find x5 to 3 decimal places. Now this is in GCSE, so if you did do pretty well in GCSE, you should remember how we do this. Now I'm going to show one of them to show the examiner I know what I'm doing. I'm saying that x1 is equal to 1. And so this means that x2 would be, using the iterative formula, the cube root of 3 of x1, which is 1, plus 3, plus the cube root of x1, which is 1, okay? And then I'm just going to put that into the calculator. Now, the way I put this into the calculator is I would type 1 into my calculator, and then I would press the equals button. And then on my calculator, I'm going to type in this. I'm going to do 3 answer plus 3 plus the cube root of the answer. Now, if I do this, I will just be able to keep hitting the equals button, and I will get all of the different values that I've got here. So I'm just going to set that up on my calculator. I'll do 1 and then press equals. And then I'm going to do the cube root of 3 answer plus 3 plus the cube root of the answer. That's going to give me my next value for x2, which is 1.1929 ... And because it's stored in my calculator, I can literally just press the equals button again, and it will put that 1.9129 back into the formula. So x3 is 2.1530 ... I'm going to do x4, which is 2.2070. You can see how it's getting closer to our 2.222, and x5 is equal to 2.219. And what did they want it to? 3 decimal places, and this is to 3 decimal places. Now, if you wanted to, I've seen some questions like this in the past. They ask you to say, what is it correct to 3 decimal places, without having got, say, this part that we've got up here. If you wanted to do that, you can literally keep pressing the equals button until you end up with a number that doesn't change, and then you know that it's correct to 3 decimal places. So it's almost there, but not quite. Oh, now what I'm going to do is have a look at these staircase and cobweb diagrams. So when you have a staircase or cobweb diagram, if you want to try and work out what this is where you have the iterative formula. So the red part is the iterative formula, which is the part on the right-hand side. And the blue part is just y equals x, which is always the left-hand side of the iterative formula. This just x. So we have y equals x, and then the red part is the actual iterative formula that is on the right-hand side. Now, these two are going to be these two that are down here. I'm just going to have a look at these two examples. So the way that you do this, to do a staircase or a cobweb diagram, you draw from the start value on the x-axis. You go to the curve, then y equals x, then the curve, then y equals x, and you keep doing that. If it moves towards the intersection, it converges, and if it doesn't, it diverges. And this produces 2 different shapes. It either produces a staircase or a cobweb shape. And I'll just show it using these diagrams here. So we're going to go vertically up. We're going to go straight up to the curve. Then we will go to y equals x. Then we go to the curve. Then we go to y equals x. Then we go to the curve, y equals x. The curve, y equals x. And you can see this is forming like a cobweb pattern. It looks like a spider web. So this is an example of a cobweb one. And it's also converging, okay? It is converging because it's moving in towards it. If I had one and it kind of went away, it would be what we call a diverge. So for this particular one I'm going to do, I'm going to go from here to the curve, then to y equals x, the curve, y equals x, the curve, y equals x, the curve, y equals x, etc. And each of these things is an iteration. It's like a stage of iterations. We've got like 1, 2, blah, 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 blah. And so this one is an example of a staircase diagram that we have here. And I've barely seen them ask about this before, but let's now see how we can do it for part E. It says show using the diagram, which is showing y equals x, this part here. And what's the other part? And the right-hand side of the iterative formula, this part, that's the part that's drawn in red, that the iterative formula converges for x1 equals 1, briefly explaining your reasoning. So for x1 equals 1, if I draw a line up, let's see if I can do it even neater than this. Let's see if I can get it as a vertical line. Perfect. So it's going up to the curve, and then we can see it is going to go across. I don't know why it's so wonky, that one. That's really annoying. Let's see if we can get it going across. Sort of. And then up. you can see from the aid of this diagram, when it's going back and forth, it is converging and it is a staircase diagram. So for part E of this question, you should just have vertical and horizontal lines, even though mine aren't like this. So the diagram shows a converging staircase pattern. Now, I don't know if they've ever said what's the difference between the staircase and the cobweb, but I would definitely describe this as a converging staircase pattern because it is going into the root. If you had something that is going to go away from the root, then it would be completely different. It would be diverging. So a student attempts to find a different iterative formula and correctly produces this one that we've got here. Now, this one, if you did want to check it, it looks like what they did for this one, going from the original part, is it looks like they wanted to make this x the subject. So they put all of this thing onto the left-hand side, leaving us with the x cubed minus the cube root of x. And then they divided it by 3 and subtracted the 1. They divided it by that 3 and subtracted the 1. So they came up with a different iterative formula. This is a correct iterative formula. They are going to start using a value of x1 as 2.5. By use of the diagram, which shows y equals x, and again, y equals this right-hand side part, explain whether the iteration will converge to the root alpha or diverge. So we're going to now do, instead of a starting value of 1, we are doing a starting value of 2.5. So from 2.5, I'm going to go straight up to the curve. And then from the curve, I'm going to go across to the line. And then from the line, if I can draw this neatly enough, we can see it's getting further and further away. This staircase diagram, if this curve kept going, it's going to go further and further away from the root. This is the root that we are looking for here, that 2.222. You can clearly see that this staircase is getting bigger and bigger and is diverging. So we just need to answer that question and say for part F of the question, explain whether it will converge to the root or diverge. I would say it diverges as shown by the diverging staircase diagram. And actually the diagrams help you decide where it would actually work. You can see if you did say 1.6 or something, or maybe 1.75, it would go to the curve. Oh, it's going to go down here. It's not going to be so good. So this doesn't look like a particularly good one. Maybe 2 would work. No, I don't know. So you can use this diagram to try and think where it would go that would make it kind of converge to it. It doesn't look like it's going to be a particularly good iterative formula because lots of the places appear to diverge away from this particular bit. Okay, the Newton-Raphson method may be one of the easiest parts of maths. They throw it in just as an extra opportunity to do some differentiation. They give you this in the formula book, so there's not really anything to memorize. We're just going to dive straight in with this question. Again, it's about finding roots. So f of x is equal to x squared sine x plus x minus 3, and x is between 0 and pi. The figure shows a sketch of y equals f of x, where x is measured in radians. By taking x naught as 1 as a first approximation for the root of f of x, apply the Newton-Raphson method once to obtain a second approximation for the root of f of x, giving your answer to 3 significant figures. So all we need to do is use this formula. We are going to be saying our next approximation, which is going to be x1, because we started with x0. They sometimes start with 1 and sometimes start with 0. It would be, using the formula above, this. So it looks like, even though I did a huge dash symbol there, just the only thing we need to do before we get started is we need to differentiate f of x to find f dash of x. So if f of x is x squared sine x plus x minus 3, let's differentiate it to find f dash x. Now this is going to need to use the product rule. So we have that u is x squared and v is sine x. If you're doing further maths or you've done loads of revision already, you probably don't need to do it like this. But obviously x squared goes to 2x and sine x goes to cos x. And for the product rule, we get these things multiplied. So that's going to give me the x squared cos x, and it's going to give me a 2x sine x. X differentiates to 1, and minus 3 is not kind of used at all because it differentiates to nothing. So if I want to find the next approximation, this is using this formula that we've got up here. That means that x1 is going to be x0, which they've told us to use as 1, minus f of 1 divided by f dash of 1. So it's 1 minus, now I'm just going to be subbing 1 into these two things that we've got here. It's going to be 1 squared sine 1 plus 1 minus 3 divided by the f dash part. So it's going to be 1 squared cos 1 plus 2 times 1 sine 1 plus 1. It's just a matter of typing this carefully in the calculator. So 1 squared is 1, so I'm just going to do 1 minus sine 1, make sure that bracket closes afterwards, plus 1 minus 3, over cos 1, close that bracket, plus 2 sine 1, plus 1. And I get 1.3594 blah 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 to 3 significant figures is 1.36 to 3 significant figures. And actually this looks like it's pretty much in the right kind of place. So we started off with 1, and this looks like it's probably somewhere around 1.3, 1.4. And I just want to say, if we did want to interpret this as a diagram, if we needed to interpret a diagram for the Newton-Raphson method, we draw a tangent to the curve at the first approximation to the root, and where it crosses the x-axis is the second approximation. So at 1 that we've got here, this is the point where x equals 1. If I was going to draw a tangent to that line, it should look something like this. And where it crosses the x-axis here, this is our approximation to the root. This is our approximation x1. Okay, this was our x0, and now we've got our x1 approximation. And again, if you wanted to do it, you would then go to this point, you draw a tangent, and it should get really, really close to that point if you were going to do another approximation. So thank you so much for sticking through these videos. Good bits of revision in these. The next one's going to be a big one. It's going to be integration. So I hope to see you in that video.